Good morning, everyone. As introduced, my name is Jason Yates, and I'm the Technical Services Manager for Riello UPS Limited. Today, we're going to be looking at smart grid-ready uninterruptible power supplies, basically becoming partners of the energy transition. Now, just to give you a little bit of background about Riello UPS Limited, we are basically the UK subsidiary of the Italian-based Riello Elettronica Group. Now, Riello Elettronica is an uninterruptible power supply manufacturer with the well-known brand Riello UPS. Now, the energy represents the group's core business, and in particular with the manufacture of UPS that are able to guarantee the quality of the electrical supply to critical loads and maintain power continuity in case of blackouts or anomalies within the electrical system. Now, Riello UPS designs and produces UPS solutions for every kind of requirement, from banks to hospitals, transport to infrastructure, from small domestic applications up to large-scale data centers. And we have two R&D facilities, one located in Legnago near Verona and one in Comano in Milan. Now, these are dedicated to the development and testing of UPS. Now, Riello UPS always looks to improve product performance by continuously innovating, so much that today Riello UPS now has over 32 lines of UPS products specifically for energy management, based across a broad range of technological architectures. Now, what am I going to talk about today? Well, first of all, I'm going to talk about and just explain what are smart grid-ready uninterruptible power supplies. We'll also take a brief look at some of those applications in that whereby using a UPS system as a potential grid frequency stabilizer. We'll also look at UPS for peak shaving or voltage stabilization or waveform correction. In conjunction with those, we will also look at the use of UPS with lithium batteries, supercapacitors, and for power storage. And then we'll finish off by briefly looking at the future of UPS and things that we're going to be changing in the UPS industry in terms of efficiency and silicon carbide. So first of all, what is a smart grid-ready UPS system? Well, a smart grid-ready UPS system basically is a UPS that has the potential to, firstly, most importantly, communicate with the local power systems. Therefore, this enables them to basically potentially help stabilize the grid, store energy using either lead or lithium batteries. They can peak shave, or they can force the load to go off grid. They can be used to voltage stabilize or optimize. They can be used to waveform correct or power factor correct. They can be integrated with solar systems. Obviously, they need to operate at high efficiencies. Basically, UPS have the potential to play a big part in the ever-evolving energy network and provide advanced interconnectivity and communications, effectively turning a UPS system into a virtual power plant. So just to show you one of the projects that we did, this was a project that we did for a grid frequency stabilizer. Now, this project was done in conjunction with RWE. Now, the brief for this project was to enable data centers and large power users to become partners of the energy transition. Now, obviously, transition to a decentralized zero carbon system requires obviously increased flexibility from demand and generation, along with frequency regulation to compensate for low synchronous generation. Now, obviously, data centers and large installations can contribute to the energy transition as prosumers. Now, the Master Plus system that we developed is a specific UPS battery solution, which was designed to both profit from the energy markets without taking any of the energy market risks, whilst at the same time provide reliability increases via an advanced UPS, 24/7 monitoring, and an extended backup time. Now, the system that we developed comprised of four key parts. Now, the first part was obviously a highly efficient UPS system. Second was the cycle-proof premium batteries. Then we had the integrated control system, and we obviously needed a route to market contract. So The key part was obviously the UPS system. Now, the photo there on the screenshot was the 200 kilowatts test machines that we put into the pilot project in Germany. Now, these two machines which were developed for this project are obviously smart grid ready. They offer smart grid communication protocols. They're true online UPS systems. They're highly efficient. They're a unity power factor machines, so the kilowatt and the kVA are the same. They're full IGBT and DSP based technology with high fault and short circuit capacity, multiple power options for flexibility, parallel mode for resilience and capacity, and obviously they're built on existing resilient and proven technology, and they offer full galvanic isolation. Now, obviously, a UPS system is nothing without its battery system. Now, the particular battery system that we use for this project were cycle-proof premium lead-acid batteries from a well-established producer. Obviously, for this kind of application, we could also use lithium, as this would also be a viable option. The main benefits of this system was that it offered significant space saving because it was a very compact battery arrangement. There was sufficient battery capacity for the critical equipment support and also for the commercialization purposes. The system had real-time battery monitoring for predictive maintenance and also intelligent battery charge and discharge control. Now, the battery system itself was effectively split into two virtual parts. The first part was the backup segment, and the second part was the commercial segment. Now, the backup segment of the battery basically represented around about 30% of the total usable capacity. Now, this particular part of the battery is obviously controlled and configured by the UPS system, but it could not be accessed by RWE, and therefore the backup segment is primarily preserved for the critical load only. The remaining segment of the battery was the commercial segment. Now, the commercial segment represented the remaining 70% of the total usable capacity. Now, this capacity, again, was configured and controlled by the UPS, but this time, RWE did not have access, only had access to this section, and therefore the commercial segment is used for the grid stabilization and, if required, for the critical load. Now, typically when the system is operating, the state of charge of the battery, as you can see there, generally oscillates somewhere between 60 or 70%. And therefore, if there was a main supply failure on the site where this system is installed, the site will typically have access to an extended backup autonomy because obviously they have the use of their guaranteed backup segment plus any of the remaining commercial segment. Now, obviously, with the UPS and the battery system was a requirement to have a fully integrated control system. Now, here, this system was basically the integrated control system's priority was to monetize the solution within the energy markets. Obviously, it had to provide a high IT security design. The priority of the UPS is obviously always to protect the critical infrastructure on site. And during a main supply disruption, the system only supported the critical load, and so therefore they could not apply any commands to the system. Basically, the Master Plus, being the system it is, effectively is a standard UPS installation, and therefore it can be integrated into an existing infrastructure. The final part of the project was obviously the route to market. Now, the way the project was developed, so RWE and Riello provided a system to participate in the energy markets, with all of the energy market risks actually being taken by RWE in terms of the grid frequency response and grid cost avoidance. Now, the benefits to the site owner was that they received a significantly discounted battery, along with extended warranty on all main components, remote control and 24/7 monitoring, preventative maintenance, extended backup time, and potentially reduced grid charges. In return, RWE simply got the usage rights for the commercial section of the battery. So how did it work? Well, this is the data that is taken from one of the live systems. As you can see, the blue line represents the grid frequency. The red line represents the power demanded from the system. And the yellow line represents the power that's being provided by the system. So therefore, as you can see, as the frequency increases above 50 hertz, effectively what we do, we take power from the grid and push that power into the battery system. Then when the grid frequency falls down below 50 hertz, we take the power back from the battery and we push that back into the grid again. And therefore, we help to try to stabilize the grid by either taking power from the grid when the frequency is high or pushing power back into the grid when the frequency is low. And therefore, the UPS system then operates for frequency response, so therefore to try to balance the grid frequency. Now, that was just one of the projects that we did with a Smart GridReady UPS. Another project that we've done for Smart GridReady UPS was a UPS being utilized for load peak shaving, for voltage stabilization, and waveform correction. Now, for those of you who are not familiar, effectively peak shaving is where we utilize a UPS to effectively limit the power that's being taken from the main supply. And the way we do that is if the load on the output of the UPS system increases beyond the set or the predefined level, then what the UPS system does, it takes a portion of the load from the main supply and the remaining portion of the power from the batteries. So therefore, the UPS system can effectively peak shave the load that's been applied onto the incomer versus the load that's actually being connected to the output of the UPS. Now, typically peak shaving modes of operation, there's typically 4 of them. The first one is a static load, whereby the UPS input has a fixed and defined level, and therefore the system just sits there and actually peak shaves to that set point. You can take that one step further, whereby the user can actually control and decide when the UPS system limits that power, and this command can be pushed through to the UPS either via volt-free contacts or Modbus TCP, etc. You also then have impact load buffering, whereby this is similar to peak shaving, but it can also operate in that if you've got a system where you've either got a weak source or weak generators, anything like this, if you have a site whereby you have a large impact of load in one step, then the UPS system can effectively buffer and slow down the rate of change of that load onto the incoming main supply. And finally, and probably the most commonly used, is the dynamic peak shaving, whereby the system works automatically in line with the site conditions. And just to explain and expand upon this a little further, this would be a typical dynamic peak shaving application, whereby, as you can see there, you've got the incoming grid onto a site where you have power metering. This power metering is interconnected with the communication cards within the UPS system. You've got critical load that's connected to the output of the UPS system, so therefore battery backup is provided for that load. And also you've got the general site load. So therefore, basically what happens is as the load increases, then the UPS system can share a portion of that load onto its internal batteries instead of overloading the main incomer. Now, this was used on a site recently, whereby the contractual limit for the site was limited to 1 megawatt. Their typical site loading, normal load, as you can see, typically moved around between 500 to 900 kilowatts. And they had a critical load, which had a maximum load of around about 300 kilowatts. Now, obviously, in real terms, at full load, that would put 1.2 megawatts onto the incoming supply, which obviously would go beyond the contract. And therefore, what happened is, during these short durations, the UPS system was there to use then to push that portion of power onto the batteries. And therefore, when the power coming into the site was low, we could use that power to charge the batteries. And when the power coming onto the site was high, we could take the power back from the batteries. So that's a good example of where we've used dynamic peak shaving. Another function of UPS is the UPS as a voltage stabilizer. Now, sometimes people refer to this as voltage optimization. Now, I don't know if you're not familiar with an online UPS system, but that is a typical diagram of an online dual conversion UPS. We call it a dual conversion because basically it's we take the main supply comes in, we convert the AC to DC, that's our first conversion, and then we reinvert the DC back to AC again, and that's our second conversion, hence the term dual conversion. The term online basically means that the load is being permanently powered from the inverter. Now, one of the benefits of an online dual conversion UPS system, they have a very wide input tolerance in terms of voltage and frequency. Now, as you can see there, typically a UPS system will have an input tolerance of around plus 20% down to minus 10. But at lower loads, or if the UPS is oversized, that tolerance can be increased to plus 20% down to minus 40%. But one of the key benefits of that is no matter what happens to the incoming supply, the UPS will always deliver a predefined, in this case, 400 volts AC with a tolerance of plus or minus 1%. And therefore, the benefits of this is that a an online UPS system can operate as a true voltage stabilizer, and also, if required, can be provided with or without battery backup. It doesn't need to have batteries connected to do this. Benefits of this: obviously, the load is always powered from the inverter, VFI, which VFI stands for voltage and frequency independent. Basically means whatever comes into the UPS is not passed to the connected load, and obviously that operates with a very precise tolerance. Basically, a UPS system is a perfect power conditioner and or for voltage stabilization application. So that is another good thing that again this can be dynamically controlled. Another thing that a UPS system has, a smart GridReady UPS has a function, is waveform correction. Again, this is the typical diagram of an online dual conversion UPS. In this case, however, now we have two power flows. We have the power that is flowing into the UPS system via the rectifier, and also we have the main power that is passing currently through the bypass line. Now, in this mode of operation, the UPS operates on bypass, but the inverter is running, and what's happening there is the inverter is actually operating in parallel with the bypass in order to correct the waveform that's actually being applied to the incomer. So, for example, if we applied a load, these are only representative figures. If we applied a load to the output of the system, in this case, it's got a high total harmonic distortion of the current, THDI, of greater than 30%, with a low power factor. Because the way the active power waveform corrector is working, basically what happens is the system is now corrects that waveform. As you can see now, that has now reduced that down to around 6%, and obviously improve the overall power factor. Now, obviously, in reality, the performance of the system will change depending on exactly what it is we're supplying and exactly what tolerance it needs to meet. One of the key benefits, it's still a UPS, so it can still provide full battery backup with zero breaks. So in the event that there was a mains failure, it could still provide full battery backup. And then once the main supply is returned again, return back to waveform correction mode. Benefits of this, they can significantly reduce the harmonic contents being applied onto the main supply. It's an active input power factor corrector, so you don't need any power factor correction systems. And in this mode, because it's operating in bypass, it can run highly efficient at 98.5% efficiency. So they are just a few of the smart grid-ready applications that we can use UPS for. One of the upcoming things, obviously typical UPS systems at the moment most commonly are supplied by lead-acid batteries, but we are making the move now to look at alternative technology in terms of lithium batteries, supercapacitors, and obviously being utilized for power storage. Now, this is a typical lithium battery system that we supply. Obviously lithium batteries are improving all the time. There are some pros and cons, obviously, for lithium battery. Pros, they're lighter, they're more compact, they've got a higher power density, greater flexibility. They can have high discharge and recharge rates. They can operate in high temperature tolerances. They've got a longer lifespan and increased number of cycles. Consequences, obviously, management of the lithium is critical. The vendor-specific BMS systems, which I'll touch on in a moment in a bit more detail, it's more expensive, but their prices are coming down. And obviously, the inherent safety concerns. Now, a lot of people are saying, are they the real substitute for lead at the moment? Well, I'll leave you guys to decide that, especially when you've got the likes of pure lead batteries, which also may be an alternative. But we'll see how the markets pan out. Touching on the UPS communication with the lithium system, and this was saying about the BMS specific communication protocol. You can buy a lithium battery system which you can connect directly onto a UPS system without any problems, but the problem is with that, it's not a fully integrated package, and therefore we developed a system whereby the UPS system can correctly communicate with the lithium system, because under certain conditions you want the UPS system to stop charging or charge or do certain things, and therefore it's imperative that the lithium system is fully integrated with the UPS system, not purely just for the control of the lithium, but also for the monitoring and the information that the UPS system is putting out to the outside world in terms of the autonomy times, the recharge times, and so on and so forth. So it's important to have a fully integrated system. Another mode of power storage are supercapacitors. Now, supercapacitors offer an eco-friendly alternative to the traditional battery-based system. They have high power density. to deliver autonomy in a range of seconds. Now, when I say a range of seconds, they can operate anywhere from 5 seconds up to a couple of minutes. So they're ideal for sites prone to very short interruptions or where they have rapid online generation. They obviously can offer a high number of cycles. A supercapacitor can have 1 million or more cycles compared to around 300 of a typical lead-acid battery. They offer long terms of total cost of ownership savings over battery monitoring, replacement, recycling, and disposal. And obviously, they can operate over a very wide temperature range in terms of, down as low as -30 up to plus 45 degrees C without any need for any intensive air conditioning. So supercapacitors, again, are improving all the time and is becoming a viable option for energy storage. Now, in terms of the energy storage systems, obviously, again, this is becoming more and more hot topic. This is a typical energy storage system. This is a UPS system that's being used in conjunction with PV arrays, both on the input and on the output. It's still a UPS, so it still offer protection against the various issues on the electrical system in terms of blackouts, overvoltages, frequency variations, power surges, voltage distortion, and so on and so forth. But therefore, it can still be utilized to back up critical infrastructure. Basically, the way the UPSs are going these days, UPS are playing a bigger part and a key role in the energy storage market. And as more and more demand comes along for this, more and more developments are being made in the UPS sector. So where are we going with UPS systems? Well, to finalize, the main thing about UPS is efficiency. We want to have UPS systems which are as efficient as possible. Efficiency obviously plays a key role in UPS, and the biggest change to the marketplace that we're seeing coming through at the moment is that silicon carbide components now make it possible for UPS to achieve over a 98% efficiency whilst it's in online operation. The benefits of silicon carbide components is now that they're becoming more readily available, their use throughout many industries becoming more and more common. Again, the high efficiency these components provide significantly reduces the overall cost of operating a UPS and increases the overall performance of the UPS system. And in conjunction with this, the reduced losses means that the less heat is produced by the UPS system, which in turn means less cooling on site. So effectively, the UPS systems of the future, you will see more and more coming through with silicon carbide options, and eventually it will all be silicon carbide as the price comes down and the availability increases. So that's an overview of smart grid-ready UPS systems and some of the battery storage systems and some of the overall where we're going in the future. And so I will open the floor up to any questions.
Perfect. Thank you so much, Jason. There's currently no questions from the audience, but the one question I do have, based on the fact that we have a panel straight after this regarding microgrids, is where could a UPS potentially sit in a microgrid situation?
Oh,
did I stump you there?
Yes, there's a few areas where you could they could be used, and obviously, like I say, the points I've covered at the moment only
virtual power
are only a few. They're actually real at the moment. They exist.
Yeah.
I suppose it depends on the application, to be honest with you. Okay. There's so many things there could actually be. And if somebody does have a specific application, it's something we can most certainly look at. You know, because we have full design and control of the UPS system. The UPS system can do many things. A lot of things that people don't actually realize they can do. But yeah, there's lots of parts it could play part of in terms of microgrids.
Also, how much revenue could you potentially earn from a virtual power station?
Oh, I knew you were going to ask me this. I knew this. This is an RWE question. I can find out, and I will. If you want, I can present some kind of information and data. Yeah, this is an RWE. I knew somebody was asking me this. I should have got an answer to this question. But yeah, I'm not entirely sure, to be honest with you. But I'd have to ask RWE on that front because we don't actually deal with that side of it.
Okay, that's fair enough. And also, we do have a question from the audience. Mark Perez says, what are the features of SiC that help with efficiency, and why are these just emerging now? Is it advanced manufacturing / 3D printing of SiC?
Yes, I think it's everything. Obviously, silicon carbide back in the day was extremely expensive. The technology didn't exist. It's like going back the way UPS systems changed over to IGBT technology. As component manufacturers and the demand becomes greater, the components become available. And obviously, it's in terms of the development cost. Before, it was too expensive to build UPS from silicon carbide, whereas now we can actively, obviously, silicon carbide UPS will carry an increase in cost, but primarily the driving factor for us now, it is possible now to build UPS. Again, as technology changes, things get cheaper, become more cost effective. You start to get pre-built packages for bi-level and tri-level inversion and rectification. And so as the manufacturers produce these components, it becomes more readily available to all. So it's just the natural migration of components.
Perfect. Is there anything else you would like to add while we wait for more questions?
No, I'm good.
No?
No. If there's anything else anybody would like to ask?
We'll give it a few minutes. I think I'm done with my questions. Obviously, I had the obvious questions.
Yeah. Like I say, obviously, UPS system, it's changing all the time. Storage system, energy storage systems, lithium systems, and so on, changing all the time. It's continually being developed. UPS systems are getting smaller, more efficient. The main thing for us, obviously, we can only take a UPS system down as small as possible with obviously connection sizes, things like this. But that's our main driving factor. The market's ever expanding. UPSs are being used in so many different sectors these days. A UPS system in terms of the smart grid can be utilized for so many different things now. What we try to do is encourage people to actually, if they have an application, then obviously we can always look at these things in terms of whether these are possible. Everybody's next idea could always be the next greatest idea, and that's the way it goes. Obviously, because a UPS system can do many different things in terms of, providing single phase from three-phase supplies, from providing three-phase supplies from single-phase supplies, from balancing power, single-phase power across three-phase supplies. There's so many different things that a UPS system can do. So it's just an ever-changing world.
They're pretty versatile technologies, and it's getting even more versatile.
It is, yes, it is. And because, again, obviously the requirements from more vendors is that we need to obviously offer more communication protocols, more control, and obviously develop new systems utilizing power. We've done many projects. I haven't covered them here. We've done many projects in terms of things like car chargers, whereby we store energy in containerization to enable dealers to provide high power car charging in the daytime. So we charge overnight, or we use PV in the day, and therefore we can utilize UPS in terms of energy storage for high power car chargers and things like this. There's lots of things that we do, which again is more and more people are demanding more and more, because again, infrastructure isn't quite there yet in places. Yeah. So therefore there are options available to people, and it's not just a case of a closed book. There are options.
Yeah, I guess most people just assume UPSs are there for emergency power, but
precisely.
They do so much more.
I think two of the biggest things are, yes, people don't understand the potential for UPS, and in terms of the UPS systems themselves, especially with the RWE project, is technology is far more advanced, and I think it's people's reluctance at the moment to trust the technology. But I think over time that will come, especially with the ever increases of energy at the moment.
Yeah, definitely.
So
perfect. Thank you so much, Jason.
All right.
For your time.
No problem whatsoever.